Your computer's processor, the CPU, is an absolute beast at crunching numbers. But have you ever wondered how it knows the story behind those numbers? How does it know if a result is negative or if it's hit exactly zero? Turns out, that context is everything. Today, we're going to pull back the curtain on the CPU's secret little scorecard that makes all of this possible. I mean, really think about it. When a CPU calculates, say, 5 minus 10, the result is -5. But how does the CPU know that? How does it understand the concept of negative? Or when you're comparing two files to see if they're identical, how does it know they're a perfect match? See, it's not just about getting an answer. It's about understanding the outcome. And that's where the computer's secret weapon comes into play. And the answer? Well, it's this incredibly elegant little component called the flag register. The best way to think of it is as the CPU's own internal scorecard. After every single calculation, and I mean every one, this register gets updated with these little bits of information called flags. Each flag tells a tiny piece of the story about what just happened.
So, to really get how this scorecard works, we need to meet the team of specialists that live inside it. Let's start with the flags that track the most basic, fundamental nature of any result. First up on the team, we have the sign flag. Its job is super simple but absolutely critical. It's the positive or negative detector. As soon as a calculation is done, this flag takes one look at the result and tells the CPU whether the number is positive or negative. And here's the clever part. If the result is negative, the sign flag gets set to 1. If it's positive, the flag is cleared to 0. This isn't random. It's directly tied to the very first bit in the binary result, what's known as the most significant bit. In the world of signed numbers, a 1 in that spot means negative, and a 0 means positive. Simple as that. Okay, our next team member is the 0 flag, and I like to call this one the annihilation expert. Its mission is singular, absolute, and kind of dramatic. Did the last operation result in a total wipeout? Did it all go to 0? Its job is just brilliantly simple. If the result of a calculation is exactly 0, the 0 flag is set to 1. If the result is anything else, I don't care if it's positive, negative, huge, or tiny, the 0 flag stays at 0. It has one obsession: absolute 0. So let's take a super easy example. The CPU is told to subtract 5 from 5. The answer, of course, is 0. Instantly, the 0 flag just flips on, like a little light bulb going off, signaling to the entire system, hey, we hit 0 over here. And this is incredibly important for things like, comparing two values to see if they're equal. All right, next up on our team is a specialist with let's call it a more peculiar job. It's time to meet the oddball counter. This is the Parity Flag. Now, this flag couldn't care less about the value of the result. Instead, it's interested in its structure, its binary structure. Its only job is to count up the number of 1 bits in the result and then report back whether that count is even or odd. So if the binary result has an even number of 1s, the parity flag gets set to 1. If it has an odd number of 1s, it's cleared to 0. Now you might be thinking, that sounds really weird. Why? Well, it has a key historical purpose. It was one of the earliest, simplest ways to do basic error checking when sending data from point A to point B. Just look at this example right here. The number 3 in binary is 000011. If you just count the 1s, there are 2 of them. Since 2 is an even number, the parity flag is set to 1. Yeah, it's really as simple as that. Okay, now for our final group of specialists. These are the guardians, the lookouts. Their entire job is to scream a warning when the CPU is about to push the boundaries of its mathematical world, when things get too big to handle. First is the carry flag, and the best analogy for this is the odometer in your car. You know, when you've driven 99,999 miles and it clicks over, all those 9s roll over to 0, and that 1 rolls over to the next spot. The carry flag does exactly that for binary math, specifically for unsigned numbers. It's the signal that a number got so big it just wrapped around. And right beside it, working as its partner, is the Overflow Flag. This one is the logic error guardian. It watches for results that just don't make any sense in the world of signed numbers. You could call it the CPU's built-in common sense checker. Now, this table is super important because these two flags get confused all the time. Just remember, the carry flag is for unsigned numbers. It's just the odometer rolling over, no big deal. The overflow flag, on the other hand, is for signed numbers. It catches things that are logically impossible, like adding two big positive numbers together and somehow getting a negative result. That's a huge red flag that the number got too big to fit, and the overflow flag sounds the alarm. So, We've met the team: Sign, Zero, Parity, Carry, and Overflow. But why does this tiny little scorecard matter so much? Okay, this right here, this is the aha moment.
So why does this all matter? Here it is. Because every single decision your computer makes, from the simplest if-then statement in a piece of code to the most complex logic in a video game, is built on the status of these flags. They are the absolute bedrock of decision-making in all of software. Here's the play-by-play. First, the CPU does something, like comparing two numbers, which under the hood is really just subtraction. Second, that operation automatically instantly sets the flags. If the numbers were equal, their difference is 0, right? So the 0 flag flips on. Third, the program checks the flag. It literally asks, hey, is the 0 flag on? And finally, based on that simple yes or no answer, the program branches. It chooses which path of code to run next. And that is the whole magic trick, right there. These flags are the mechanism that allows the CPU to basically react to its own work. It's not just a dumb calculator mindlessly crunching numbers. It can perform an action, check the outcome using these flags, and then decide what to do next based on that outcome. So there you have it. These are the unsung heroes working inside your CPU. The sign flag, telling us positive or negative. The 0 flag, the annihilation expert. The quirky parity flag, counting the bits. And our guardians, the carry and overflow flags, protecting the system from its own limits. This tiny little team makes all intelligent software possible.
Every single time you click a button, load a web page, or play a game, this invisible team of flags is working tirelessly, making literally millions of decisions every second. It kind of makes you wonder, right? What other invisible, elegant systems are powering our world, working away right under our noses? Some to think about.